The Paranal Observatory in Chile boasts one of the world's most beautiful views of the starry night sky. It was here in 2009 that a surprising discovery was made regarding a particular star. This star is 1,000 times bigger than the Sun and is covered in bright red flames. It also has a bump-like protrusion. And that's not all.
As I said, it can be very close to collapse and final explosion. It can be even at an age of 99.9% of its life.
We are in Hida City in Japan. The star may explode any day now, and preparing for this is a gigantic observation device called Super Kamiokande. It should detect signs of the explosion faster than anywhere else in the world.
もしもし、超新星爆発のアラームが鳴りましたので、至急会議を始めてください。
If signs of an explosion are detected, telescopes around the world will turn to the star. The star that's capturing the attention of astronomers worldwide is the red giant in Orion. Betelgeuse. It's thought the explosion at its death will be 300 million times brighter than the Sun. Furthermore, it is only 640 light-years away. On the grand scale of the universe, it's a short distance from Earth. Some scientists warn the explosion may even spell danger for Earth.
If it is going to produce a gamma ray burst and we're looking straight down the jet of radiation.
Betelgeuse, the red giant. What is happening now on this star? And what will happen at the moment of its death? We investigate Betelgeuse, a star on the brink of death. Roppongi, Tokyo. The city at night, viewed from the top of a 240-meter-high skyscraper. The city nightscape is not the only view to be enjoyed. Guides are on hand to explain the stars in the night sky.
初めて。ああ、よかったです。
月がある日でも見えるのがあの星ですね。わかりますかね。ちょっとオレンジ色、そうオリオン座ですね。ちょうど今東の空でオリオン座がで目印が赤い星と右の方に白い星がありますよね。明るい2つの星がオリオン座なんですよ。これは東京でも確実に街の中で見えるんで、ぜひ晴れたら毎晩見えてます。
With the city's bright lights, it's not easy to find the constellations. But there is one constellation that stands out more than the rest. Orion. It's identified by the 3 stars in a row and the 4 bright stars surrounding them. In ancient Greek mythology, Orion was a brave hunter armed with a club who died and ascended to the heavenly skies. Today's show features the bright red star on the top left corner, Betelgeuse. We begin by looking at the position of each star that makes up the constellation. The stars appear to be on the same plane, but in fact are at widely varying distances from Earth. Betelgeuse is 640 light-years away, making it Orion's second closest star to Earth. 200 years ago, an odd discovery was made about the star. It took place on the Cape of Good Hope, on the southern tip of Africa. The British established an observatory here in the 19th century. At the time, accurate positioning of the stars was vital for navigating the seas. The observatory was built to study the stars visible from the southern hemisphere. The British astronomer Sir John Herschel was fascinated by the bright Betelgeuse and recorded observations of the star. Herschel noted the stars in order of brightness and noticed something rather strange. These are the results of 4 years of observation. Orion here refers to Betelgeuse. In March 1836, Betelgeuse was the 4th brightest star, yet 8 months later in November, it was the brightest. He discovered that sometimes the star grew dimmer, and other times brighter. Why did its brightness vary? So began the quest to unravel the mysteries of Betelgeuse. "80 years later in 1920, a new discovery was made. This time, it was at the Mount Wilson Observatory just outside Los Angeles. The physicist, Albert Michelson, thought the varying brightness of Betelgeuse was perhaps caused by changes in its size. Michelson attached a device called an interferometer to the end of a large telescope and attempted to directly measure the size of Betelgeuse. An interferometer uses 2 mirrors to reflect the light from a star, and then combines the 2 beams. When the mirrors are close together, stripes known as an interference fringe pattern appear on the star's image. As the gap between the mirrors widen, the stripes gradually fade. The stripes disappear completely when the 2 mirrors are exactly aligned with the outer edges of the star. The distance from Betelgeuse is known, and so it's possible to calculate its diameter from its angular distance at this point. From these observations, Michelson concluded that Betelgeuse was a giant star 300 times larger than the Sun. But the mystery of its varying brightness remained. It was about 40 years later that the puzzle was solved. Guy Perron is researching Betelgeuse at the Paris Observatory. Perron uses results from the latest observations to explain the size of Betelgeuse in the following way.
Alors le Soleil, c'est une étoile qui est assez petite, qui serait par exemple de la taille de ce ballon-là, alors que Betelgeuse elle-même est beaucoup plus grosse et serait de la taille de la Tour Eiffel, et c'est beaucoup plus facile de pouvoir en voir les détails à la surface.
Detailed observations suggest Betelgeuse's diameter could be as wide as 1.4 billion kilometers. That's 1,000 times greater than the Sun. Placed at the center of our solar system, it would surpass the Earth's orbit and reach as far as Jupiter. What's more, it has changed in size by more than 100 million kilometers. The giant star changes its brightness as it pulsates. In fact, this pulsation foreshadows the star's future fate.
Qui présente l'intérêt en fait d'être une étoile très brillante, donc facilement observable, et aussi d'être une étoile en fin de vie. Et donc il y a des phénomènes extrêmement intéressants dans son environnement et sur l'étoile elle-même qui méritent et suscitent l'intérêt des astronomes pour son observation.
Fixed stars, which shine by their own light, are born and die just like humans. Stars are born out of clouds of gas floating in space. The gas gathers under its own gravity, and when its core temperature hits 10 million degrees, it starts to shine. And a star is born. A star spends most of its life shining constantly in its steady phase. The Sun is presently in this stage. But even the Sun will eventually reach the end of its life and gradually expand, turning red. This is when a star becomes a red giant. With a star like Betelgeuse, whose mass is more than 8 times the Sun, it expands even further as it draws nearer to death and becomes a red supergiant.
Parce qu'on sait que sa durée de vie est très limitée. Et que, contrairement au Soleil, par exemple, qui a vécu la moitié de sa vie, Betelgeuse en a probablement vécu 90% ou 95%.
Betelgeuse is coming to the end of its life. Scientists around the world are carrying out research to reveal the giant star's true shape. Keiichi Onaka is based at the Max Planck Institute for Radio Astronomy in Germany. Since moving to Germany in 2000, he has been studying dying stars. In 2009, Onaka made a surprising discovery about Betelgeuse's shape. He made his observations at the Paranal Observatory in Chile. At an altitude of 2,600 meters and with 350 clear nights per year, it is the ideal location for astronomical observation. Pattern.
この真ん中の列なんですけども、ここのところにですね、この列にはこう縦に こうしましまがあると思うんですね、縦に。でそれがまあコマごとにちょっと少しずつ動いてるんですけども、これがですね干渉計で観測した時に得られる干渉島というやつでして、星のですね大きさとかその形に関する情報っていうのはこの干渉島の中に含まれているわけです。
What drew Onaka's attention was this part. There is a kink in the black stripe. Further investigation revealed something unexpected. Normally, spherical stars produce symmetrical graphs. In Betelgeuse's case, however, the left side of the graph is significantly raised. What can this mean? Onaka grappled with this conundrum for 6 months and finally reached a conclusion no one could ever have imagined.
どうやったらこの観測データを説明できるかといろいろやってみた結果、やっぱりそういうふうにここの星があって、その一部にまあコブというかですね雲みたいなものがあって、それがこうもっと上の方に動いていると。でそういうことがないと観測データが説明できないというのが分かったわけです。
Onaka concluded that the asymmetry in the graph was caused by a bump sticking out of Betelgeuse. Onaka explains the star's shape that he uncovered from the observation results.
これがベテルギウスの星でして、でその上にこういうコブというかですね雲、大きな雲ですね。で大きさがですねベテルギウスの星自体の半分ぐらいの大きさですね。でそれがですねこう上の方に、この雲は上の方にずーっと動いていると。でずーっと言ってみますと、実際にはですね秒速の10キロが15キロというものすごいスピードでこう複雑にランダムな動きをしているわけですね。
So Betelgeuse is massive, 700 million kilometers wide and 40 million times bigger than the Sun. And unlike normal spherical stars, it has an irregular shape because of its bump. But what caused this huge bump to form? One scientist is proposing that the answer lies in the star's interior. Andrea Chiavassa from the Free University of Brussels is using not observations, but calculations done on a supercomputer to try and decipher the mystery of Betelgeuse's bump. He has calculated how heat travels out from the center of the star and how the gas moves over time. This is how Betelgeuse looks according to Chiavassa's calculations. Its surface is covered in patterns 800 million kilometers wide, and here and there, pockets of gas rise and then sink back down. According to Chiavassa's calculations, the heat generated inside the star has created convection currents hundreds of times wider than the Sun's diameter. Of the two stars. The gravity at the surface is quite low as it's so far from the center of the star. Gas carried up by the convection currents rising at great speed is what's creating the bump.
Après, il tend à se détacher de l'étoile. Donc notre étoile, elle nous apparaît plus ronde, mais toute une forme comme une patate.
Betelgeuse's odd shape was caused by the star expanding with age and by the sheer force of its massive convection currents. In 2006, Akari, a Japanese infrared astronomy satellite, was launched. Using infrared invisible to the naked eye, it can survey clouds of gas and dust that float in space. These are images of Betelgeuse captured by Akari. Let's combine these 4 images taken with different filters. This reveals a spherical cloud of gas and dust enveloping Betelgeuse. It is 3 light-years wide, 20,000 times greater than Betelgeuse's diameter. The huge amount of gas and dust that can be seen here is thought to have been emitted by Betelgeuse. But it was unknown how Betelgeuse expelled so much gas and dust. Trying to decipher this mystery is Perron of the Paris Observatory. Perron set about observing the area around Betelgeuse and the gas it emits. But it's not an easy task to magnify and examine the area surrounding Betelgeuse. This is because there is turbulence in the Earth's atmosphere. When there is turbulence, the image is distorted, making it hard to accurately capture the gas and dust that the star emits. Perron solved this problem with a clever idea.
This is a lucky imaging experiment. This card here will be the star, and the pool here will be the atmosphere with random motions, and that destroys the image quality. So we would put the card in the water and try to take the best image possible. The technique of lucky imaging consists in taking many pictures until we get the right picture where the turbulence, or here the pool, is the most stable possible, so that the image is the best possible. And we repeat that for many times during the night.
Perron calls the image taken the exact moment there's no turbulence the lucky image. Let's look at the actual photos taken. Continuous shots are taken at a high shutter speed. In every few hundred photos, there is one clear image with no distortion. This is the lucky image that Perron is after. But in reality, the light from a star is limited. To take images at a high shutter speed, you need a gigantic telescope that can gather a large amount of light. So Perron headed to the Paranal Observatory in Chile.
There are some other big telescopes like these ones, but this is a unique place in the sense that we have 4 telescopes in the same observatory with a multitude of instruments that can be used, so that you can make every observation you would think of in modern optical astronomy.
This is the observatory's Very Large Telescope, or VLT for short. With mirrors 8.2 meters in diameter, it's one of the world's largest telescopes. Using this, it's possible to capture at high shutter speeds the faint gas surrounding Betelgeuse. Perron checks the images freshly captured by the telescopes. Perron and his team have also devised a way to pick out just the lucky images from the million images of Betelgeuse. They turn their attention to the brightest part of the images. When an image is distorted by the atmosphere, light is scattered and the image is less bright. So by comparing the brightest spot of each image and choosing only the brightest images, Perron's team can separate out all the lucky images. Furthermore, by combining all the lucky images, it's possible to capture even the faintest, smallest detail. This is the face of Betelgeuse that Perron unmasked from his million images. The orange ball is Betelgeuse, and the blue veil is the huge quantity of gas and dust released by the star. At last, we have an image that captures the star expelling gas and dust into space. Unexpectedly, the gas and dust are not emitted in a concentric circle, but in 3 different directions. The furthest tip extends 4 billion kilometers from the star. In terms of the solar system, this is about the distance between the Sun and Neptune. The image also revealed that a clump of gas and dust had broken off from the outer edge. This was how Betelgeuse was releasing the high volume of gas and dust that the infrared satellite Akari had captured.
Alors c'est la première fois qu'on met en évidence en fait cet environnement-là avec une image d'aussi grande précision. Alors ce que l'on voit là, en fait, la première surprise, j'allais dire, c'est que l'étoile est bien ronde, donc ça c'est tout à fait normal, et on s'attendait à avoir un environnement autour de l'étoile qui était également à symétrie sphérique. Et en fait, on voit qu'il y a 3 directions privilégiées, avec de la lumière ici, là et là.
The red giant, with its swelling bump, expels a vast quantity of gas and dust into the space around it. The dynamic activity of the star betrays how close it is to the end of its life. The death of Betelgeuse is drawing ever closer. What will happen when it dies? Hans Thomas Janka has spent 25 years researching the final years of a star at Germany's Max Planck Institute for Astrophysics.
Ja, Mittwoch wäre auf jeden Fall günstiger, ja.
Janka uses an experiment to simulate the death of a star.
We'll do a little experiment of how a supernova works, how we think a supernova works. Small container, which I will fill, and then we put some water in, and you see what happens is, of course, that there's sparkling bubbles coming and gases, and then we will see how it evolves. There's pressure building up, and in the end we will see whether the lid stays on this small container or not. So we see this is the way how we think explosions work.
Janka believes Betelgeuse will also be unable to withstand the immense pressure and will finally explode. The massive explosion of a gigantic star is something the universe has seen countless times in its long history. 1987 saw a massive explosion of a star in a neighboring galaxy, the Large Magellanic Cloud. The explosion of a star has great repercussions for us. Fixed stars like our Sun emit light as a result of nuclear fusion taking place in their core. A star is mostly made up of the simplest of the elements, hydrogen. The high temperature and pressure inside a star's core cause hydrogen to fuse into helium. This creates energy, making the star shine brightly. This is the present state of our Sun. After a star has shone for a long period of time, the hydrogen in its core is eventually exhausted. And then, instead of hydrogen, the helium start fusing with each other. This produces carbon, oxygen, and other new elements. The core temperature rises, and the star begins to expand. And so begins its transformation into a red giant like Betelgeuse. Finally, when iron is created, the nuclear fusion stops. The star can no longer support its own mass and starts to rapidly collapse. The pressure in the star's core becomes so immense, it causes a massive explosion.
When the shock wave moves out of the surface of the star, we call the phenomenon the supernova event, as observers see it and as we can see it as a spectacularly bright celestial phenomenon.
When a supernova explodes, the huge amount of energy generated creates elements heavier than iron and scatters them all around. The elements created by the star float about in space. Over a long period of time, elements gradually gather together once more. And out of these, planets like Earth are born, and furthermore, life in its various forms. It's all thanks to the explosion of a dying star that we are here today.
Les étoiles, c'est des usines à atomes. Hein. Donc elle produit du gaz, elle produit de la poussière. Ici, par exemple, voilà, ça c'est de la matière qui a été faite dans ces étoiles, ou vous, ou moi, voilà. On est tous les enfants de ces étoiles-là.
This is Cassiopeia A, the remnant of a massive star that exploded as a supernova. It's possible to make out the various elements produced by the star. The red is iron, and the green is silicon. This is another supernova remnant, the Crab Nebula. The cloud of gas and dust is spreading at a speed of 1,300 kilometers per second. In this way, elements are scattered across the universe when stars explode. In all of recorded history, only 7 supernova explosions visible to the naked eye have been witnessed. The farthest away was SN 1987A, a supernova discovered in 1987 in the Large Magellanic Cloud. It is 160,000 light-years away. The Crab Nebula is the closest to us, but it's still 6,500 light-years from Earth. In comparison, Betelgeuse is a mere 640 light-years away. If Betelgeuse becomes a supernova, it would be the closest explosion we have ever faced. At such a close proximity, will the supernova explosion of Betelgeuse pose any threat to Earth? Clues to help us answer this question can be found in Argentina. It's a 2-hour drive from the northern city of San Juan, beyond the ravines. Geologists from the National University of Cordoba in Cordoba province guide us to the site.
No, está contigo. Llega hasta la cima. Y si vos continúas el perfil, cuando el cielo ve, hasta abajo, mira, allá ese estrato de allá.
Aquí estamos viendo estratos que se formaron aproximadamente entre los 450 a los 440 millones de años. Esto representa la parte superior del Ordovícico, un periodo que tiene registro en gran parte del mundo y donde se produjeron grandes eventos globales.
400 million years ago, dinosaurs had yet to roam the Earth. Apart from some moss growing on the ground, few life forms existed. Vakari has found something.
¡Wow! Mira, Juan.
It is a fossil of a trilobite. At the time these strata were formed, the sea was full of many different organisms, and trilobites in particular flourished. There were species that lived deep in the sea, and others that lived near the surface. The sea was full of trilobites of all different types. When trilobite fossils from different geological strata are compared, an interesting fact comes to light. In strata more than 440 million years old, both deep sea and shallow water species are found. But in strata less than 440 million years old, only deep water species are found.
Esta extinción así tan particular es realmente misteriosa porque, insisto, es como, ¿por qué ser tan selectivo? ¿Por qué solamente tiene que haber pasado que incidiera y produjera, digamos, una extinción masiva de los grupos de trilobites que vivían en la columna de agua.
One scientist believes that a supernova explosion caused the extinction of the shallow water trilobites. Brian Thomas is an astrophysicist at Washburn University in America.
At the Ordovician extinction about 440 million years ago, the most abundant life was trilobites. The main reason for that is that the ozone depletion is a radiation event which directly affects the organisms.
When a massive star explodes as a supernova, it releases a powerful burst of radiation in the form of gamma rays. Using theoretical calculations, Thomas can show what changes occur to the Earth's environment when hit by a burst of gamma rays.
This figure here shows the depletion in ozone over the globe. So there's a rapid drop-off in the ozone layer, and that reaches about 30 to 35% total. And that will increase slowly, recovering over about 10 years.
Here is what Thomas thinks happened to the trilobites. Earth is protected from the sun's powerful ultraviolet rays by the ozone layer. When gamma rays produced by a supernova explosion hit Earth, the ozone layer is destroyed. This allows the sun's harmful rays to beat down on the land and the surface of the sea. Thomas believes this killed off all the trilobites near the surface of the sea, but those deeper down, where the UV rays couldn't reach, survived.
Once the ozone is depleted, ultraviolet light from the sun comes through the atmosphere, and organisms that are exposed to this ultraviolet light will have their DNA and other molecules like proteins damaged by this particular radiation. That can cause death.
Thomas argues that the death of a gigantic star had huge repercussions on life on Earth in ancient times. The explosion of Betelgeuse is thought to be imminent, but are we in any danger? Past research has shown that when a star dies, powerful gamma rays are released at an angle of less than 2 degrees from the axis of rotation. So the key lies in the direction of Betelgeuse's axis in relation to Earth. Observations were carried out to measure Betelgeuse's rotational axis. The Hubble Space Telescope was used to investigate the giant star. It measured the speed at which certain points on the star's surface were moving. This revealed for the first time ever Betelgeuse's axis of rotation. The star's axis misses Earth by 20 degrees.
Fortunately, if this is the pole, Betelgeuse, and it represents the way the jet would be oriented, the Earth is not directly focused along that beam. It's actually off by about 20 degrees. So that jet will go off into space and miss us entirely.
When Betelgeuse explodes, it looks like Earth will be safe from harm. What will we be able to see from Earth when Betelgeuse explodes?
At the edge, it's much more blue.
Kenichi Nomoto's team at the University of Tokyo has used theory-based calculations to scientifically show how Betelgeuse will change in color, temperature, and shape when it explodes. Here is a simulation of the results. The final moments have arrived for Betelgeuse, Orion's red supergiant. Its color changes from red to blue as its temperature shoots up. 1 hour later, Betelgeuse burns more brightly than any other star, and no one can fail to notice this change. 3 hours after the explosion, the star's brightness intensifies until it is around 100 times brighter than the All around Betelgeuse, the gas that the star emits as it dies reflects the intense light of the supernova and glows brightly. 4 months later, the star starts changing color again. As the temperature falls, it changes from blue to orange. The gas swathes the star layer upon layer like a flower in bloom. Eventually, as the
本当に立ち上がりから色の変化まで詳しく観測された例というのはほとんどありませんね。ですからこのベテルギウスがもし爆発してこういう現象が見えればもうかつてない天体ショーとして非常に面白い初めての現象だと思います。
Since the dawn of history, we have never seen a supernova explode so near. But when will this happen? In January 2011, an article became a hot topic of discussion on the internet. It claimed that Betelgeuse will explode in 2012. But no one really knows. A facility in Japan with the ability to identify the explosion before it's visibly observed is drawing attention from around the world. It is located 1,000 meters underground among the mountains of Gifu Prefecture. This is the Super Kamiokande, an apparatus that detects particles called neutrinos that fly in from space. Its tank is lined with more than 10,000 detectors. Just before a supernova explodes, a flood of neutrinos is released from the star's core. The neutrinos from Betelgeuse will collide with the water inside Super Kamiokande's tank and emit countless flashes of blue light. At the earliest, the explosion may happen just a few hours after these flashes occur. At the facility, training is being carried out to ensure they will detect the explosion.
もしもし、超新星爆発のアラームが鳴りましたので、至急会議を始めてください。
When a large number of neutrinos is detected, a video conference is held with scientists around the world, and the data is analyzed. As soon as the supernova explosion is confirmed, observatories worldwide are notified.
ニュートリノが出てから光で超新星爆発が見えるまでっていうのがやっぱり短いものでは数時間以内に起こってしまいますから、やっぱりもたもたしてると光での爆発が見えちゃった後に情報を流してもね、やっぱりその爆発の瞬間をいろいろな望遠鏡が捉えると、そういうことがやっぱり重要なことだと思いますのでね、重要でしかも面白いことだと思いますので、そういったことのためにやっぱり早く情報を流さなきゃいけないと思います。時間との戦いですよね。
Scientists around the world are waiting with bated breath for Betelgeuse to explode.
超新星爆発が非常に近くで起きるというのは10万年に1回あるかないかというくらいの稀な現象で、これがキャッチできればですね、非常に貴重な観測になる。
It's near enough to be a spectacular spot in the sky. If a supernova explodes, we will probably see it during daytime.
Oh, it would be fantastic to see that, to see such a big explosion, very bright. I would really love to see that in my lifetime. Absolutely.
Betelgeuse has fascinated us with its bright red glow. It is a fierce giant, bearing a huge bump and emitting dust and gas with staggering force. And soon, it will meet its death in a massive explosion. When will its final hour arrive? At that historic moment, humankind will witness yet another undiscovered truth.